Hello everyone. Let's continue some loop algorithms. There's a few more assignments left in this class, and then we're pretty much done. This next assignment is Major League Baseball players. It's really a data analysis assignment where we're going to be parsing through a large data set and calculating some certain statistics from it. This is probably arguably one of the harder assignments in this class. So the reason why it's arguably the harder one is because it's applying a large loop algorithm and expecting folks to parse a large data set. So we'll talk about this on Wednesday, but today we should be able to finish lesson 17 and possibly the lab 17 too. All right, once again, loop algorithms. Just for another high-level overview, loop algorithms is probably one of the biggest takeaways in a programming class. It's a big takeaway because it enhances problem-solving skills, right? Skills where you can represent solutions as a series of steps. This is the part where your creative problem-solving skills can increase, right? Or not increase at all. I'm hoping it'll increase for most folks. The one way to increase your creative problem-solving skills is to kind of try out writing stuff out yourself and looping over it. All right, so for example, we're going to load up lesson 17 and lab 17 right now. Let's see. So lesson 17 and then also the lab 17. So the parts where we can exercise our creative problem solving skills is in the lab. Most folks are on the recording. And once again, if you're on the recording, I highly suggest trying it out yourself before seeing the solution. Because here I'm just going to kind of go over them, and I'm hoping folks will pause the video before seeing the solution. Okay, so I hope that kind of makes sense on the creative problem solving skills, because if you just copy down everything like word for word, it could possibly hurt your problem solving skills. So let's try to exercise some loop algorithms today. Well, we're gonna kind of jump back and forth between here and the lab, right? The lesson and the lab. And then once again on Thursday we'll jump into a Major League Baseball players assignment. Right? This is really just asking you to write a loop to go through a large file and calculate statistics. And then just looking ahead, well, there's another assignment. It's called Major League Baseball players again. This one is a variation. Right? It's using a library called Pandas. Pandas is you can think of it as a way of making data science easier. So this one is really going to be doing automatic things that our previous one did. Okay. Cool, let's jump into it then. So we're continuing this lesson 17. Last week we got a sneak peek into the lesson 17. Or we got a sneak peek into some reduction algorithms. And once again, we already did this on Wednesday last week. Reduction algorithms, you can think of it as taking a sequence and producing a single value from here. And so we did that last week with a couple examples, like finding the average of a list, right, or summing up everything in the list. And we can see that in the top part of the lab. So here, let me go to the top part of the lab 17. We practiced some reduction algorithms. We did the sum, right? Get a sum and iterate through it to calculate the total. But we did something called the max and the min as well. So the max right here, we wrote this in a function instead. But yeah, this is also a reduction algorithm. right? The function is taking a sequence of values, and then it's collapsing it down to a single value, which will return. In this case, it's just returning the max of all these values, right? So if my list were to be this, then the reduction algorithm should collapse to 239. And I need to run it in the right order. So let me load this function in again. And yeah, there we go, right? It collapses down to 239. And there are a bunch of print statements here. These are just debugging statements that come from the function, which is supposed to help us visualize every step along the way. All right, so hopefully people are cool with this so far. Let's do one more reduction algorithm and then jump into the rest of the lesson. And so as a quick warm-up, let's do the opposite of that previous question, right? The previous one was asking us to find the maximum. All right, let's find the smallest element now. All right, once again, we're in the lab. We're on the lab 17. Let's write a for loop that prints the smallest element in the list. So I'm probably going to do this in a function just to have a little more practice, right? Like say we had the imaginary function minimum value. Right, say we had that function minimum value and we were to pass in my list. Right? But minimum value is supposed to represent a function that reduces this list into a single value. Right? In this case, it should reduce it down to 1. All right, so if we were to print this out, it should print 1. Right? But it's not going to print anything out yet because we didn't define the minimum value function yet. So here, I'm going to go ahead and attempt to define it. Right, once again, if you're on a recording, I highly recommend trying this out yourself first. Right? So do we have a function called minimum value, and then it takes a list. Right, I'm just going to call the list numbers. Okay. Okay, so what's one way we can do this? There are so many different ways. Well, one approach we saw last week was something called a high watermark algorithm. Right? A high watermark algorithm pretty much keeps track of the biggest wave in the sequence. So if we were to go back to the previous question, we were asked to do the largest element. The high watermark algorithm says something like, okay, we're looking at 1. This is the highest number so far. Right? And then go to the next one. This is now the highest one. And then 3.4, this is now the highest. And 239, this is the highest. And then 43, this is not the highest. So the high watermark remains at 239. And then we go on to the next ones, 18. It's not greater than the previous one, previous 239, right? And then so on. So pretty much one way we could do it is by updating it when we beat the previous value. I mean, not the previous, the current minimum. Right, so here, let me initialize a current minimum to something, right? Because once again, the goal is to initialize the current minimum equal to something, and then in the end we could return it. And then in the middle, I'm going to put a to-do here. Right? I'll do this in just a bit. The to-do is update current minimum. Or update current minimum, meaning that we're going to look through the sequence and then update it, right, if we beat it. Right? What should we initialize the current minimum to then? There's multiple ways, right, multiple things you can initialize it to. Right? Some folks might choose to initialize it to the very first number. Right? So some people might initialize it to the very first value here. Right? You can say, hey, the first value is the minimum, and then now look through the rest and see if it beats it. Right? So that's what some people would do. Some might also initialize it to, I think, some very large number, right? Like maybe they might say, oh, current minimum is equal to 99999, right? So some large number, and saying that, okay, now we're gonna look through all these sequences and see if they're less than it. Right? Same thing. Right? You could do some large number like positive infinity. I think earlier here we used negative infinity. Right? You could use positive infinity as well. Or you could initialize it to the first number. Right, so here I'm gonna choose to look at the first number, number 0. Now this is saying initialize our low watermark to the very first number. Right, and then we can look through the whole sequence and see if it beats it. Right, if it beats it, well, we should update the current minimum. Okay, so let's write a loop. So I'm gonna write a loop for number in numbers. Right, once again, the left side is singular and the right one is plural, right? Because the right one is the sequence and the left one is a variable that represents a value. Okay, so the goal is we want to look through at each number, and if we beat it, right? If we beat the current minimum, right, we could represent that by saying if number is less than current min, right? This is saying we beat it, so we should update the current min to whatever we have. Right, people see what this is saying? So let me just put a print statement in here real quick so we can kind of visualize what's happening. Right, like let me just put a print statement here. This is like debugging. Last week we did cover something called a debugger, but we barely went into it. For this class, print statements are sufficient for debugging. Okay, let me zoom in a tiny bit more. There we go. So once again, I'm just going to put in some debugging statements. I'm going to say looking at number, then number as an f string. And then if we beat it, we could say found a new number. Right? Found a better minimum. Found a smaller minimum. And then I'm going to put the number here again. Right, this will help us visualize what's happening. Okay, so let me load this function in and then invoke it in this bottom testing cell. So I'll go ahead and run it. Okay, so see what's happening here? We invoke the function, right? It looks at all of the numbers, but none of them beat a current minimum. Yeah, that doesn't make sense because our current minimum was the first value here. Right? So we're looking at every number, but none of them satisfy the condition. Right? 2 is not less than the current minimum. 3.4 is not less than that, right? And so on. But if we change the order of things, maybe we will see how this is being updated, right? Like let me put like a negative 5 here, and then maybe in the future I'll put in like negative 20 here. Okay, so the minimum here should be negative 20. Right, but let's see how the algorithm works, right? We should see kind of 2 different updates happen. Okay, so let me run this. Okay, there we go. I just ran it, and we should have some debugging statements. Right, it says, looking at number 1, right? Does 1 beat the current minimum? No, right? So we did initialize our current minimum to the very first element. Right? So 1 is not less than 1. Right? So then we're going to look at the next number. Is 2 greater? I mean, is 2 less than the current minimum? Right? Current minimum? Nope, it's not. Right? 2 is not less than 1. We'll look at negative 5. Right? Is negative 5 less than the current minimum? Yes, it is. Right? Negative 5 is less than negative 1. So then we're going to say, oh, found a smaller minimum. Right? So there we go. Right? We found a smaller minimum, and we're going to update it. Right? So the current minimum becomes negative 5. And so people kind of seeing what's happening here. Right? We look at 239. Right? 239 is not less than the current minimum. 43. Negative 20. Negative 20, this is less than it, so we're going to update it. right? And then finally, we'll get to the end of the loop. Right? And at the end of the loop, we're just going to return the current minimum. All right, people cool with this so far? Min and max. Okay, so we just finished doing the minimum value algorithm. Okay, looking down the lab, these are different types of loop algorithms that we need to cover. In particular, this one's a mapping algorithm. Right? A mapping algorithm wants us to take a sequence and produce another sequence from it. Right, so let's go ahead and go back to the lesson. Okay, so back to the lesson. Okay, so we just finished talking about reduction algorithms. We did some averages, we did summation, we did find the minimum, find the maximum. All right, let's go down to filtering algorithms. This one you might find useful for the next project. Right, the next project is Major League Baseball players. It's going to ask us to go through a large data set and kind of calculate some statistics. Right? In particular, you're going to want to choose your favorite team, meaning that you can think of it as a filtering algorithm. Right? Like given a large data set, maybe you want to look at certain people only, right? Certain people from specific teams. And so this is going to help us out a lot. All right, once again, think of the left side as a very large data set of every single Major League Baseball player. Right? And then think of the right side as you're filtering it to your team, right? Like you only want to look at certain people. Right? So yeah, that's a filtering algorithm, right? You can think of it as a for loop that takes a sequence and produces another sequence. In this case, we're not really modifying the original list, or we're creating another sequence. So the original one remains untouched. We're just creating a brand new one. So let's do a very small example of a filtering algorithm. Right? Like say we had a list of numbers. I'm right here. Right? And say our goal was to kind of create another list that filters numbers that are less than 20. Right, so here, let me see. What happened to my mouse? Yeah, so once again, imagine that we have a list here, and we want to produce another list, right? And that list would only have 1, 9, 12, and 15. And that's kind of the goal of this filtering algorithm. Right? So we could visualize the steps of it. This table is kind of just showing every single iteration. Right? It's kind of saying on the right side we have an output. Right? The output starts as a blank list, and then when we iterate through the original list, we're gonna populate this output. Right? Like for example, is one less than 20? Yes, it is. So we're gonna populate it, put it inside of here. Right? And we're looking at 23. Right? Is 23 less than 20? No, it's not. So our output remains at 1. Right, 46, is this less than 20? No, it's not. 92, nope, it's not. Is 9 less than 20? Yes, yes it is. All right, so since 9 is less than 20, we're gonna populate the output list again. And then finally move on to the next ones. Right, is 12 less than 20? Yes, it is. So we're gonna populate that. And then finally 5, right, 5 is less than 20. So our final output list will be here. And then we can return it. Right, so that's kind of what a filtering algorithm does. Now let me apply it here. Right, so say we had a function, or here, let me imagine that we called it. So I'm just gonna invoke the function that we don't even have yet. So it's called less than 20. And here, let me store this in some some variable. Right? This way things are a little easier to read. I'm just going to store it in some variable called test list and put it inside of this function. All right, so once again, the goal of this function is to produce another list. Right? It's not to modify this list right here. Because if we were to modify this original list, it's kind of dangerous, right? Because you're modifying original data and you might not want to, right? So it might be safer to create a copy. And yeah, this should return another list. So if we were to print this, right, like print filtered list is, right, this is supposed to just return a list. All right, so let's go ahead and define this because yeah, we don't have this function yet. So I'm going to create another cell above, right, and define a function called less than 20. Okay, I'm gonna name the argument numbers. All right, once again, you can name it whatever you want. Okay, let's go ahead and start this. So seeing this tracing in this table, right, we start off with an empty list, and then we iterate through the original list and start populating this output list. So we should probably declare a empty list. I'm going to call it output. So I'm going to declare an empty list called output. And once again, the goal is to return this output in the end. That's the goal. We're going to populate that list inside of a loop. Okay. So yeah, let's start iterating. Right? We need to iterate through the sequence. So I'm going to say for number in numbers. All right, for number in numbers, we should check to see if it matches the criteria. All right, in this case, our criteria is less than 20. Right? We want to add numbers, we want to append numbers that are less than 20. So we need to represent that condition. Right? So if something, in this case, that condition would be if it meets that criteria, right? If number is less than 20, then we can append it to the list. All right, once again, we can append with a list function called append. People cool with this so far? So yeah, there's our filtering algorithm. And let me just do some debugging statements. All right, once again, you can use this debugger, but there are quite a lot of buttons that you might have to get used to. So I'm going to stick with plain print statements for now. Like I'm just going to print looking at number. This is to sanity check every step of the function. Okay, and if we meet the criteria, then we can say something like found a number less than 20. And then let me put the number here. Okay, there's our debugging statement. Let me press play and then invoke the function. Okay, there we go. So I just invoked the function, right? And we see our final print statement is 19125, right? Which makes sense because there are only 4 numbers that meet this criteria, right? 1, 9, 12, and 5. Right? So yeah, you can see these in the debugging statements. Right? It's pretty much tracing through every single step. Okay. Once again, this is a filtering algorithm. It aims to produce a brand new list. So folks might think that our test list is touched. It's not, right? Test list is not touched because our function creates a brand new one, right? And we never overrode this test list. And so if we were to, here, let me get these debugging statements out of here. So if I were to print out the original list, like right after, see, original list is, and then original list is test list. Oh, I need to rerun this function. There we go. All right, people kind of see what's happening. All right, our original list remains unchanged because our function created a brand new one. This is kind of a safe practice because when you're doing large data analysis, you might want to treat the original data as read only. Right? In this case, we're treating this original one as read only, and we're creating a copy. Right? This is kind of safer because you're not really modifying old data. Right? You might want to preserve the old data for future. People cool with filtering algorithms so far? Okay, so that's a filtering algorithm. All right, let's do a mapping algorithm now. Okay. A similar concept, we take a sequence and we're producing another sequence from it. Right? You can think of it as we're creating a brand new one. Right? So imagine that the input remains unchanged, but our output is the same size, but just different values. And these mapping algorithms are good when you're converting a bunch of things to another thing, right? Like in terms of the next assignment, right? Once again, the next assignment is looking at Major League Baseball player stats. One of the stats will be, height in inches, right? So imagine the left as a bunch of people's heights, right? Like, oh, this guy's height is something inches. This guy's height is something inches. Maybe you might want to convert it to another metric, right? Like maybe you want to convert it to meters for some reason. Right? In that case, you would map the inches to meters, right? So we'd have a brand new sequence that we can do stuff on. So yeah, that's kind of one way we can do it. Okay, let's do a small example where our goal is to double that list, right? Like say we had a test list, right? And our goal was to put this in an algorithm and create another list that's the same size but double values. So here, let me just copy this over. Once again, say we had a test list equal to here. Right, if we were to pass this in a function called double list, right, it should create a brand new list, right, and then return it. Right, meaning that if we were to print it, it should be the same size, but everything's doubled. Right, so the mapping algorithm, one way we can visualize it is in this table. Right, we could think of it as we can create an empty list and start populating it one at a time. Right, for example, let's start with an empty list. Okay, look at one. Okay, one, we need to double it. Right, so we'll double it and append it to here. Right, and then next we look at the next number, right, 23. Right, 23, we should double it and put it and append it. Right, and so on. Right, so on. 46, double this. This is 92. So then we're going to append this. And 92 will append this. This is 184. Now people kind of seeing what this is doing. So here, let's go ahead and implement this mapping algorithm, right? Because double list isn't defined. So I'm going to create another cell up here and define a function called double list. And I'm just going to name the argument as numbers. You can name it whatever you want. Okay. So we could start the output at an empty list, right? Like remember how here at the start of the algorithm, right? Start with an empty list. So yeah, let's do that. I'm gonna call it output is equal to some empty list. Okay. And once again, the goal is to return this brand new list, right? This way the caller can have access to it. So I'm going to return output here. Right? In the middle, we're going to have to populate that. And so we do need to iterate through the sequence. So for number in numbers. Right, let's go ahead and iterate through the sequence. Right, so every number, right, we're gonna have to double and then append it to this list. Right, there's no criteria to check. Right, earlier we did some if statements. Right, we don't have to do that here because we're gonna append the number regardless. Right, we just got to make sure to double it. So we do need to double it, right? Number times 2. There we go. We doubled it. And now we need to append it to the list, right? So we could put output, append, and then this whole number there. Right, there we go. Let's test it. So I'm going to press play, and then press play here. And there we go. Right, a doubled list is this right here. Right, this is our brand new output. Okay. Well, once again, our original list remains unchanged. Right, this is a big takeaway from here, because if we change the original data, you can consider it losing data. In this case, we didn't change it. We treated this original list as read only, and then read from it, and then kind of created a brand new one. So just to prove it wasn't touched. Right, original list was a test list. All right, so yeah, original list remains unchanged. All right, people cool with this so far? Okay, so yeah, once again, this is a mapping algorithm. Okay, let's bring things a little together before we move on to the searching algorithm. So let's kind of look at a high-level overview. Imagine we're looking through a large data set, right? And maybe you only want to look at certain values of it, right? So maybe you could filter that large data set and only care about certain things. In terms of the next project, we're going to be choosing your favorite team. So maybe let's say you like the Giants, right? The SF Giants. Then you'd want to look through every single Major League Baseball player and create a new list, right? A list of only the Giants. Right? So that's one way. Right? And then maybe you could use this list for something, right? Like in the mapping algorithm, right? Maybe there are some values that you want to map to a different unit, right? Like let's say some Major League Baseball players are stored in the metric, and maybe you want to map them into a different, like the US metric. Right? So this would be good for doing stats. Okay. So yeah, people cool with this so far? Okay. Let me look at the lab real quick. Okay, let's do one more, and then we should have enough to get this rest of part 1 done. Let's do one more algorithm. It's called a search algorithm, or more specifically, a linear search. A linear search is defined as we're going through a single dimension and looking for something. All right, like let's say we had a bunch of numbers here, right? A sequence of numbers, and maybe our goal was to see if this number exists in here, right? Like it does exist, right? 23 does exist. So our linear search was successful, right? Meaning that this whole should return true. Right? So once again, this is kind of like the in operator, right? Like you might remember a while ago, we talked about a Boolean operator called in, right? Like, say we had a list of hello world and Bob, right? This is a sequence, right? And there was an operator called in. Right? So I could do something like is world in in here, right? So this is saying, hey, is this element in the sequence, right? True, yes it is, right? Or how about, let me go, is Charlie in here? Is Charlie in here? False, no. All right, so how is this working? Right, there's some magic behind the scenes, right? The magic is something called a linear search, right? Python is actually looping through this list, right? It's saying, hey, is Charlie in this first element? No. Right? Is Charlie in this next element? No. Is it in here? No. So since it searched through the whole sequence, right? It didn't find it, right? So the result is false. Right? But here in the world, right? Let's trace through this, right? Is world in the first element? No, it's not. Okay, is world in this next element? Yes, it is. So since it is equal to that element, right, we can finally return true. Right, so people kind of see what a linear search is. Linear search kind of just compares a value with every value in the sequence. Right? That's a linear search. So let's break this down. Right? Let's let's pretend that we were going to manually write a loop that will implement this. Right? So like, let me just put a test list in here. So let me imagine to invoke this. Oh, let me see. Is there a place I can put a? Okay, I'm just going to put it down at the bottom of the cell. Right, there are multiple ways we can kind of implement this, but here, let's do one way. So, say I had a test list. Test list is equal to here. Right, and then, say we were to invoke a function that we don't even have yet. Right, search, like let's say I'm searching for the number 3 in this test list. Right, the goal is it should return false. Right, 3 doesn't exist in here. Right, so this should return false. Right, and then let's say we were to do another one. Right here, let me just print this real quick. Once again, I'm printing it because the search function is supposed to return a value. Right here, let me just do another one. Right, let's say we were to search for the number 23 inside of the test list. 23 does exist in here, so this should return true, which I'm going to print out here. Now people kind of seeing the goal of this function, right? The linear search. So there are multiple ways we can apply this. Right, I'm gonna look through up here. Right, the lesson starts off with a naive solution, and then it moves on to more efficient ones. Right, so let's do the naive solution first, and then a more efficient one later. Right, basically, the naive one does a lot of unnecessary work. Right, it's doing something. I mean, you can visualize the steps here, right? But basically, we're starting off with a variable, a Boolean variable false, right? And then we can update that, right? If we find the correct element, then we can update it to true. Right? So, for example, Booleans starts at true. I mean false, right? And then if we were looking for 23, right, we can compare 23 with this first one. Are they equal? No, they're not. So output remains false. And then we're going to go to the next element, right? Is 23 equal to this one? Yes, it is. So we can update the output Boolean to true, right? So now it's going to remain true for the whole iteration. Right? But this naive algorithm is looking through the next ones, even though we don't really need to. Right? It's saying, hey, is 23 equal to 46? No, it's not. Right? Is this equal to 46? No. I mean 23? No. Right? And so on. So yeah, it's pretty much kind of naive because we changed the Boolean when we found it, but now we're looking at the rest when we don't need to. All right, so here let's kind of implement this first, and then we'll improve it in just a bit. All right, basically, it's doing a lot of work we don't need it to do. So let me go ahead and define a search algorithm. Okay, it takes 2 arguments. Right, the first argument, I'm going to call it the target. Right, it's the thing that we're looking for. Target, and then the next one is the list. So I'm going to call it like a sequence. right? You can call it whatever you want. I'm keeping it super general, right? It doesn't have to be numbers, or it could be strings as well. So I'm gonna keep it a sequence. All right. So the naive algorithm would initialize a Boolean variable, right, to false, right? It's saying, hey, we haven't found it yet. And then we can go ahead and return the output in the end. Right? The goal is when we find the target, right, output will change to true. Right? That's kind of what's going to happen. So let me go through a whole sequence, right? I'm going to say for elements in sequence, right? We're going through every single element, and we need to find a reason to change this output to true. Right? Output is a result. So the reason here is if we find it, right? If the target is equal to the element, right? This means we found it. So we could change the Boolean to true. People see what that's saying? Okay. Cool. So then we'll run this and then run it here. Right? And yeah, there it is. Right? The first one is false because it doesn't exist. The next one is true because it does exist. Okay. So once again, this is kind of inefficient because we're looking at every element, right? Like here, let me just do a print statement in here. Let me just do print. I'm looking at element. Right, so let me run that. Right, you see the unnecessary steps, right? On the first iteration, right, it's looking at 23. Okay, actually, it makes sense for the first one. It makes sense for the first one because it never finds one, right? But then looking at the next one, right, we're looking for 23. So here, let me just comment this out so it looks easier to read. Right, so I'm just gonna comment that out. Start 23. All right, look at element 1. Yes. This does not equal it, so it's going to remain false. Right? And then 23, we're going to revert it, right? Because they equal each other. Right? If target is equal to element, right, we're going to update it. So we update the Boolean here, but then the algorithm is unnecessarily checking the rest of the elements. Right? We don't need to check the rest of those elements. So hopefully people kind of seeing where this is leading to. Okay, and just real quick, there is room for a pitfall here. Some folks might accidentally do an else statement here. Right? So some folks might do something like else output equals false. Right? This is not what we're going to look, not going to produce the right result, right? Because it's going to change output to false in the later iterations. Right? So this is not what you want, right? Because if we were to so the first one does work here, right? If we look for 3 in here, right, it does return false, right? But this next one, right, this one returns false when it shouldn't. You see how at the end it returns false, right? It shouldn't. So hopefully people kind of seeing why, right? The reason why is because if we found an element, it should remain true, right? So if we're looking at the next elements, there's no need to change it to false anymore. Okay, hope that makes sense what's happening here. Okay. So to make this a little more efficient, right, you can just return true in here. Right? So instead of setting a Boolean, you can just terminate the function. Right? So return true means to quit the function and then return true back down to whoever called it. And that's pretty much it. So here, let's test out the efficiency of this algorithm now. So I'm gonna run it for this one when we're searching for 23. Right. So now it's gonna cut down the iterations massively. Right? We look at element 1, that is not what we're looking for. Look at 23, that is. So it's going to terminate the function. Right? This we're gonna terminate. We're gonna return true, and go back down to the caller, which is the main. This testing cell. Are people cool with this so far? Okay, and technically we don't really have to set this output variable. All right, well, we don't really need this because this last return statement returns false regardless. Right? So we could actually get rid of this output boolean and just return false here. Right? This is saying if we went through the whole sequence, then we didn't find it. Right? So return false because we didn't find it. Okay. I'm hoping people are cool with this so far. So yeah, returns false, returns true. There we go. Are people cool with this? Searching algorithms. Okay. All right, let's move on to the lab then. We should have enough to get part 1 done. So I'll help folks get started. Okay, let's go to the lab. Last week we did a few of these problems. In particular, part 1, number 1. We did number 2, find the largest value. And we just did number 3, find the smallest value. We should have enough to do 4, 5, and 6 now, and 7. Oh, this one should be named 7. Wait, no. 4, 5, 5. Okay, the numbers are off, but folks should have enough to get this one done. Boldface, build HTML, a list as a function argument, and remove the smallest value. Right. We'll do part 2 later. Maybe we'll do it today. Yeah, I think we can do this. But let's spend some time finishing up the rest of part 1. Okay, here, I hope folks get started. So we left off at number 4 here, boldface. Okay, the goal of here is to create a mapping algorithm. And once again, a mapping algorithm aims to produce a brand new list. Right? It's converting one sequence to another. Right? That's the goal of this one. So this one is supposed to be a mapping algorithm, right, which aims to create another list where each element is surrounded with bold tags. All right, so yeah, so go ahead and give this a shot. If folks are having trouble with this, please do remember that you can add strings together. Right? It's possible to add strings, like if I were to do eat, right? It is possible to add things on either side, right? Like let me add the B tag. Right? See, so yeah, pretty much you can map it, right? The mapping algorithm is surrounding the element with bold tags. So hopefully people have enough to do this mapping algorithm. Okay, as for number 5, this one is asking us to create a reduction algorithm. Right? So this one is saying, hey, use the list that was created up here. Right? So imagine that this created a list. Right? This next part wants us to collapse that list into an HTML string. Right? So you'll see this. It's pretty much an HTML string with an unordered list. Right? An unordered list. You can look at the HTML list, and it's pretty much like some bullet points. So this one is asking us to create a reduction algorithm. Right? It's a reduction algorithm that collapses a list. Right? It's collapsing our previous list into an HTML string. Right? So this will collapse our previous list into an HTML string. All right, here, let me comment this up above here. Mapping algorithm produces another list. Okay, cool. Okay, and then this one, we'll probably do this one together. If you want to give it a shot, it's pretty much asking you to write a function that modifies a list. So you can try this one out later. Okay, and then number 6, this one's a little trickier. Remove the smallest value. It's a little trickier because it's kind of combining two different things. Right? It's combining a search algorithm with a reduction thing. All right, so there's two things happening here, right? There's a search algorithm. Right, this is saying to look through a sequence and find the smallest value. Right, that's the search algorithm. And then it wants us to remove it. Right, search. So it's a search algorithm, and it's also a it also returns something. Right, so a search algorithm, it's doing multiple things, right? It's going to remove the smallest value and return it. It returns it. So it's technically a search algorithm. Yeah, that's exactly what it is, actually. Okay, this one's a little trickier, but yeah, if folks could try it out, yeah, please do. Okay, let's give it like a 15-minute intermission. I'm hoping folks can at least do a couple of them, like boldface and then build HTML. Okay, so let me start a 15-minute timer. Once again, if you're on the recording, please pause it and try it out yourself. Right? It's really likely that you'll need to know how to do this without seeing the solution first. So let me pull up 15-minute timer. Okay, once again, we should have enough to do 5, right? Build HTML, and then maybe these next ones as well. Pretty much all of part 1. Okay, welcome back, everyone. Hopefully, folks gave it a shot. Now, let's try it out together now. This number 4, boldface, is asking us to map this original list into another list where every element is bolded. It doesn't ask us to write a function, but I'm going to do it anyways, just to kind of practice. And plus, our final exam will be all functions anyways. So let's pretend that we were to write a function, right? Like let's say, here, let me make another cell here, right? Imagine if we were calling, here, let me declare this list first. Imagine if we had a function called bolded items, which takes a list argument, right? So let me put items in here. The goal is this function should return a brand new list. So let's see. And if we were to print it out here, right, it should print out bolded items. All right, that's kind of the goal here. All right, so we need to write a function called bolded items. So let me go ahead and create that function. Define a function called bolded items. All right, it takes some list. Right, I'm just gonna call it sequence. Right, you can call it whatever you want. Okay, once again, with the mapping algorithm, it's generally safer to declare a brand new list and then create it from there. Right? We don't really want to modify the sequence itself because then you're kind of modifying original data. So imagine if we had an output equal to an empty list, right? This is our brand new list that we're going to populate with items from sequence. So we do need to return this in the end. And then in the middle, we could iterate through the sequence, right? For elements in sequence, our element will go through each of these strings, right? And all we need to do is wrap it in the, what's it called? The bold tags. Right? One way we could do it is just with the plus operator, right? Where we could take the element and then add something to both sides. Right? This is just one way of doing it. Right? There's other ways too. You can use an F string, you can use a formatted string, right? But we're going to surround this with a B, the bold tag. All right, so there we go. We surrounded the elements. And right now, this expression technically doesn't really do anything to the list. right? We need to add this expression to the list. In particular, an append. Right? This is, by the way, this is appending one single string. Right? It might look like 3, but no. This whole expression evaluates to one string. So we're going to append that string to output, and let's see what it looks like now. So press play here. Okay, there we go. People are seeing what's happening now. Right? Our bolded items, it returned another list. Right? So we could actually store this list into something. So here, let me just store it into like, let me store it into another one. I don't really want to call it bolded items because this is the name of a function, not really the name of a list. So I'm going to name it something else. Let's see. I'm just going to call it result. All right. So if we print out the result, then it should be same thing. Right? All I did was I stored the output. Are people cool with this? Okay. Once again, the original data remains unchanged. All right, well, we're dealing with a brand new result here. Okay, there we go. So we just created some HTML elements. The next question asks us to collapse this whole list into a single value, into a single HTML string that represents an unordered list. So this is a reduction algorithm. It's going to go through our previous one. Right? We're calling this result, by the way. Right? A result is the current one we're working with. So we want to iterate through result. Right? We want to iterate through result and build an HTML string with surrounded by unordered list. Right? So if you take a look at the previous HTML lesson, you might remember that an unordered list has a UL tag. Okay, so let me just pull it up real quick. So this is our intro to HTML lesson from several weeks ago. You might remember that the lists, the unordered list. Yeah, unordered list typically looks like this right here. Right, we start off with UL, ended off with UL, and in between it are list items. So we need to do kind of two things, right? We gotta handle the UL first, the unordered list tag, and then we need to surround every element with this list item tag. Right, so yeah, just a couple things. Okay, let's go back to the lab. So here's a lab. Right, like we do need to have a string. Right, I'm gonna call it my HTML. You can call it whatever. I'm gonna go ahead and initialize it to an unordered tag, unordered list tag. Right, and basically, this is like saying we start off with UL, right? We start off with unordered list, and then now we need to iterate through the elements and append each list item, right, surrounded by these tags. So let's handle that now. So now we need to write a loop that goes through this result. So I'm gonna go through all the results, right, for element in result. All right, we're gonna have to append this to my HTML string. Right? I think you can append, yeah, you can append the strings with a plus sign. Right? You can say my HTML equals my HTML plus. Right? This is saying add to the current HTML. Right? In particular, we're gonna add the element. Right? This is like saying append the element to the HTML. Right? So this plus this. Okay, but this element needs to be surrounded with a list item tag. So around here, around the element here, I'm gonna put the list item. All right, list item. And then another list item here, the closing tag. And just to make things more readable, I'm gonna put in parentheses. You don't need parentheses here, but it makes things look a little more readable. Right, this is saying go through each element and append the element, but surrounded by list items. Right, there we go. And then, so that for loop is handling each row, right? And then finally, we need to close the tag, right? Like the ending it with closing /ul. So I'm gonna go ahead and do that outside of the loop, right? It needs to be outside of the loop because we only wanted to do it once. So we can say my HTML equals my HTML plus the closing tag, right? That's the final one. Okay, so there we go. We just did that. Let me print out my HTML to see if it looks fine. Okay, it looks kind of fine. It's unformatted, but HTML text doesn't need to be formatted. So if we were to display this, right, let's see what it looks like. Right, this looks fine. It's just ugly. So here, let me use a display function. I think I have to import something. I think I have to import from ipython.display, import HTML. Right, this way we can wrap the my HTML inside of a HTML object and then go ahead and display it. Right, this is just to test it. There we go. See, so this HTML string, when we display it, it's an unordered list. Right, and once again, that's because we start off with an unordered list tag, right, and then we start appending elements. Right, we appended this element next, right, and then in the next iteration, we appended this element. And the next iteration, we did this one, right, and then finally, the last one, repeat. Right, and then after the loop terminates, we add the closing tag, which is where this comes from. So then we can display it. All right. Hopefully people are cool with this so far. Okay. So this is a reduction algorithm. Okay. Let's do a couple more. This next one is asking us to write a function that modifies a list. Right? It's not asking us to return anything. It's really just this part is really just showing us that we can modify lists within functions. Like, remember how earlier we talked about mapping algorithms, how they don't really modify the original list? And then same with the filtering algorithm. Right? The filtering algorithms that we did, that doesn't modify the original list, just create a new one. Right? It is possible to modify the original list, right? But I would consider this slightly dangerous because you're modifying original data, and in the future you might need that original data. So it is possible to modify the original one. Right? Let's do that real quick. Right? That's the point of this one. It's saying write a function that modifies a list by adding something to the end of it. So I'm going to create a new cell here and pretend to invoke it. Right? So imagine if we had a list. Right? I'm just going to say, I'm going to call it test list. Let me just make some strings here, like hello world. How are you? Just some random strings. It doesn't really matter. But say we were to pass this into a function called addMe, right? And say I were to add me and put like test list. Right? It is possible for this function to modify the original data, right? Meaning that it'll be changed. And if we print the test list in the end, right, we should see it different. So let's go ahead and make this function. Right? It's define a function called addMe, and it takes some sequence. Right? You can call it whatever you want. And this function is really just asking you to hard code your name to the end of the list. So it's kind of like saying, take the sequence, right, and then just add your name. I'm just going to add my name here, Andrew. Right, just a single line. Right, this is modifying the original data. Right, so here I'm going to run this and then invoke the function. Right, people kind of seeing what's happening here. Right, our original list got modified. Right, it started off with these 3 elements, but then we modified it. Right, so it's possible. Right, and once again, they're different names. Right, it's called test list, but when we pass it up here, it's called sequence. Right, they're still the same list, but in Python, you're able to still access the original elements. Right, sequence here is the test list, so we're modifying it here, and if we keep running it, right, it's gonna, yeah, it's still gonna append Andrew there. Right, so yeah, that's really all the question was asking for. It's really just showing us that we can modify lists. That's all it's showing us. But I would steer away from this. It's probably a better practice to return a brand new list. This way we're not modifying this original data. Okay, just to improve on this a bit. Actually, no, I'm not going to improve on this a bit. We'll see this later in the next assignments. Okay, and then now just asking you to apply it one more time. Right, it's saying if you had another list called a list and then pass it to add me, right, it should do the same thing. Right? It's just going to modify the sequence. So if we print a list here, right, see, it modifies this original list. All right, let's move on to the next ones. This is the last one in part 1. It's a little trickier. It's asking us to do a searching algorithm and remove something from it. Okay, so I guess we could focus on here, let's pretend like we were calling it first, so folks kind of see the point of this function. Right? Let's deal with numbers for now. Right? Say we were to have a list of numbers. I'm just going to call it test list. Right? Let's say I had a list of numbers like 5, 10, 1. Let me deal with bigger numbers. 50, 90, 10, 100. There we go. See what a test list. And if we were to call this function remove min, right, it should modify this original list. Right, it's going to modify the original list and also return the smallest value in that list. Right, so the end goal is this 10 should be removed. So yeah, let's get that started. Okay, so I'm going to write a function called define remove min. I'm just going to call it the list. Okay. So we need to find the smallest value, right? That's the goal here. And delete it later. So you might recall we can find the minimum value with a high watermark algorithm or a low watermark algorithm. Right? We did this in the beginning of class. Find the smallest value. Right? So we did this where we said, oh, the first one is the minimum, and then look for some smaller ones. Right? We could apply a similar thing. All right, so let's go ahead and find the smallest value. That's our first step. And then we'll focus on removing it later. So let's do a similar one. Let's declare a current minimum. Right, current minimum is equal to something. Right, in this case, I'm just going to initialize it to the first value in the list. Right, this is saying, hey, our smallest one is the first one. Right, and then we can start iterating and see if any of them beats it. Now that's what we could do so far. So current minimum is that. Let's go ahead and search for the current minimum. And so let's search. So I'm going to go through the list, right, for number in the list. Right, we need to find a reason to update the current minimum. Right? The reason here is if the number beats it, right? If the number beats the current minimum, then we can update it. Right? It's very similar to the previous one. Right? This is actually exactly the same as all the way up there. Right? All the way up there, we did this. This is a minimum value, right? So make sure you can do this stuff here. Okay. So if we beat it, then we can update the current minimum. Right? Current minimum is now equal to a number. Right? So there we go. And then finally, we can go ahead and return it after the loop. Right? So after the loop, right, outside of it, we can go ahead and return it. Right? This is just a start. We're not done with it yet. Right? All this does is finds the current minimum. Right? It doesn't return it. It doesn't remove it yet. So here, let's take a look at it. Right? Like if I were to print this remove minimum out, right? It's technically returning the smallest value. Right? It's technically returning the smallest value. So if we were to print it, right, it should print out. Oh, I forgot to run this cell up here. Oh, hold up. Still getting an error. This list is not defined. Oh, let's see. I have a typo here. This should be the list. There we go. Rerun that. Rerun this invocation. There we go. So I'm just sanity checking the variables. Right? In this case, we correctly found the minimum. Right? So smallest value is. Let me put this in an F string. The smallest value is 10, but we need to do one more thing. Delete that value from the list. Right? And that's what the function should do. Right? See how the function is called remove minimum? Right? It should remove it, right? But it's not removed yet. Right? Like if we print out the test list, list is now. Right? The test list is here. It's still the same. Right? We should see the 10 gone. Right? This should be deleted from here. So we need to find a way to delete it. Right? The function does find it, but how do we delete it from the list? Right? Once again, we are able to modify this. Right? There are a couple ways we can remove it. So let me put a to-do here. To-do is to remove the element from the list. Okay, we need to remove the current minimum from the list. How do we do that? So let me go back to the week 2, right, and just review a couple ways. So we covered lists a long time ago. There were a couple ways we found out how to delete something. Right? One way is we can delete by index. So let me show right here. Right, remember this delete operator? Right? It allows us to delete an element by the list. So if we delete the one at number 2, right, it's going to remove this element here. Right, so yeah, we could do that, or we could do another way. Right, another way is using the remove function. Right, the remove function doesn't use an index. Right, instead you put the element in, and then the function will search for it and then remove it. Right, so we could use the delete function, or we could use the remove. Right, this remove one is actually going to be a lot less efficient. Right, and here let's talk about why. Right, this is inefficient because it's doing a search when we already did that. Right, so basically we can use this function. Right here, let's try that. Where is it at? Right here. Right, we can use that remove function. We can say the list dot remove, and then the element, which is current minimum. Right, we can. Right, so let's see what it does. So we're going to remove it and then return that current minimum. Right, well, once again, we are allowed to return this current minimum because we stored it already. Right, we stored it, and then this function is saying, hey, look for it and then remove it. So this is going to work, right? So let me play this real quick. There we go. We played it. So you see what happened? The 10 got removed, right? So it did work, but it's kind of inefficient. This is inefficient because the remove function does a linear search, even though we already did it, right? We already did a for loop here that looks for it, right? And this remove function is saying, hey, look for the current minimum now, right? So it's actually going through this whole list, right? And then looking for the current minimum and then removing it. So it would be more efficient to use the delete operator instead. But the delete operator takes an index. So right here in the lesson on number 6, right, there was a delete operator. Right? All you need to do is give it the index of where it's stored. So the operator will not search for it, right? It's just going to go straight to number 2 and then delete it. So we can go ahead and apply that. Right? Basically, we need to find a way to store the index. Right? So this is inefficient because it redundantly performs a linear search. It's inefficient. We need to find a way to delete, right? Like we need to say delete the list, and then something in here, right? We need to put some index that represents where it is, meaning that we should probably keep track of the index, right? The index of where it's located. So in here, I could create another variable. I could say min location, right? Start off at 0. Right? This is saying, hey, our current minimum is at position 0. Right? And then if we find a new minimum, we can update that location. So location is equal to some number. Right? We do need to increment the min location, by the way. Like maybe we could keep track of an index, right? Index start at 0, and then every time we iterate, we could increment the index. All right, so this is saying it's keeping track of where we're at. Right? So if we find a current one, we can just set it to the index. All right, well, once again, the index, this is keeping track of which position we're at. And if we find a minimum, right, that position will become the minimum location. Right, so once we keep track of that, we can just delete it. Right, delete it at the min location. Right? That's the index of where we found it. Okay, and once again, this index plus 1 is outside of the if statement. Right, it's outside of the if statement because we need to increment it no matter what. All right, so let's test it. So run it, and run this. There you go. See, same thing. The takeaway here is the difference between the delete operator and the remove function. And once again, I'm just looking at the list chapter. Right? The difference here, the delete operator is an instant operation, whereas the remove function is not instant. Right? It does a linear search. It's saying, hey, does this work? No. Does this work? No. Does this work? Yes. So it'll delete it. Right? But we don't need to do this remove function because our search algorithm already finds it for us, right? This loop already does it. All right. Cool. Any questions about this so far, part 1? All right. Okay. We just finished part 1 in the lab. Oh, well, we also finished lesson 17 on algorithms. So let's get the rest of this lab done. And then on Thursday, we'll jump into some assignment hints. So here, let's do this one together. Since we only have like 15 minutes left in class, Right, let's do this together. If you're on the recording, try this out yourself. All right, part 2 is asking us to write some more looping algorithms. Right? In particular, this first one is asking us to search for a certain value. So let's kind of talk about dictionaries real quick, right? Before we talk about this function. When we're using dictionaries, we can index by its key, right? Meaning that, let's say I had a random dictionary here, right? Like let's just say I had a random dictionary of like student IDs. My dictionaries use curly braces, right? So let me just put some key value pairs in here, like let me put 1, 2, 3, 4, 5, and then say that this number responds to Alice, and let me put another key value pair, 1, 1, 1, 1, 1. Let's say this goes to Bob, and let's say there's 2, 3, 4, 5, 6. Let's say this goes to Charlie. All right, once again, this is just a random dictionary. It is possible to index a dictionary by its key. Right, so if we said student IDs, and we said something like 1, 1, 1, 1, 1, this would return us Bob, right? Because dictionaries use keys to find the value. But is it possible to do it the other way around? Right? Like, is it possible to say student IDs and put Bob in here, right, and then have it return 1, 1, 1, 1? Right? Let's see. I'm gonna run it, and it says no. Right? It can't. Right? It can't because it says there's no key named Bob. Right? This makes sense because Bob is a value. So this is a limitation in dictionaries. Right? One limitation in dictionaries is you can't find its. I mean, you can, but it takes more work. Right? But basically, you can't do it in an instant operation. Right? Like ideally, this should have gave us 1, 1, 1, 1, but it didn't. Right? I mean, we can do the other way around. Right? So hopefully, people kind of seeing the motivation of what we need to do. Right? If we wanted to find Bob's student ID, we'd have to do a linear search, right? Meaning we'd have to look at this first one, right? See, is this equal to Bob? No. Is this equal to Bob? Yes. And since it is, we can finally return the key. Now this is a limitation in dictionaries, and this is where that's what this function is asking us to do, right? It's asking us to write a function named reverse get, right? That takes a dictionary. So I'm just going to pass in the student ID's dictionary and then the target, right? Let's say we're looking for Bob, right? The goal of this function is to return the key. Right? So this should return 1, 1, 1, 1. Right, so let me print it out real quick. All right, okay, it should print 1, 1, 1. Okay, it's not implemented yet. Let's go ahead and implement it. Right, so hopefully people see the goal of this function. Right, it's to do a linear search. We're searching for the key that equals Bob. We're searching for the key that gives us Bob. I mean, okay, so let's find a function called reverse get. Okay, it takes 2 arguments, right? One is the data, and then one is the value, right? Or the target we're looking for. Okay. So the linear search here is to go through each key and check if it matches the value we're looking for. So we should probably write a loop, right, or something in data. Right? But if we use something in data, data is a dictionary, so something will actually represent a key. Right? Once again, you can see this in the previous lesson in the for loops. So in the for loops lesson a couple weeks ago, if we go through a dictionary, right, its default behavior is to iterate through its keys. So we can go ahead and iterate through all of its keys. So I'm going to rename this to key. For key in data, right, we can check if that value matches what we're looking for. Right? So we need a criteria, right? If we found it, then we can return the key. Right? So if we found it, we can say if data key. Right? Once again, this is the value we're currently looking at. Right? If that current value is equal to what we're looking for, right, then we can go ahead and just return the key. Here, let me make this a little more easier to read. It's probably easier to read if we grab the current element first, right? So this is the key. We could grab the current value, right? The current value is equal to the data at that key. Right? So this is saying grab the value. So current value will become Alice, right? And then we can check if that current value is equal to what we're looking for, or double equals. And so if this is equal to Bob, then we can just return this key, right? So return the key right here. Right? It's not going to return it because they're not equal, right? But on the next iteration, right here, let me do a print statement, a debugging statement. Looking at current value. Okay, so yeah, let's test this. I'm gonna run this here, right, and then run this, and oh, I got an error. Current value not defined. Oh, I think I spelled it wrong. Current value. There we go. Okay, there we go. So we're gonna reverse get, or we're gonna search for the student ID that's associated with Bob. Right, so there we go. We look at the current value, Alice. Okay, that is not associated with our target, but then our next value is associated. Right, so since it's associated, we're gonna prematurely return. Right, this is saying quit the function. Right, there's no need to check the next values if we already found it. Actually, there might be a need to check future values, right? Like if people had the same name, then you might want to, look at more IDs. Are people cool with this so far? So once again, if you put like Charlie here, right, it's going to return it's going to return the ID, right? But if we put someone else, like let's put Andrew, right? Andrew doesn't exist here, so it's going to say none, right? Which makes sense because the function technically returned nothing, right? It technically got down to here and then did like an implicit return none, right? That's really what it's doing here. Okay, we're cool with this so far. All right. Just a little off-topic thing. With dictionaries, it's impossible to have two keys correspond to different elements. So this is saying it's impossible for having this right here. Right? This is impossible because it's like a function, right? A function should have one output for every input, right? But in this case, we're having two inputs and one output, right? This is technically impossible. So if we were to print out the student IDs here, I think the next one gets overridden. So let me just see. Yeah, so see what's happening here, right? Bob happens, but then we're inserting another value, right? So this original one got taken over. Right, so hopefully people kind of seeing the limitations in dictionaries, right? We can do the opposite though. Like we let me add another value, right? Like it is possible to have 2222, right, be another Bob. This is possible, right? It's okay to have different keys go to the same value, right? But not the other way around. So student IDs here, right? You see both of them are here, right? There's 2 Bobs. So yeah, this is definitely possible. But if we were to reverse get it, right? Like let's say we were to do a reverse get on Bob, right? What do you think it would return? A reverse get means do a linear search and find the student ID. In this case, it would just give us 1111, right? So hopefully people kind of seeing why, right? Because it iterated through this. This is not Bob. Goes through this. This is Bob. So we're going to prematurely terminate, right? So that's what's happening here. Right? We're saying, hey, we found it, so there's no need to check the next ones. But it's arguable, right? There can be a need to check these next ones and maybe return this as well, right? That's totally possible. So this is up to your design decision, right? Your design decision is, should you return the previous one, or should you return the later one, right? Or do you want to return all of them? Right? It's totally up to what folks want to do. Right? If you want to return all of them, then you're probably going to have to declare some list. Right? So imagine you're declaring a list, and then you're going to append to that list every key that was found. Right? So yeah, it's whatever your design decision. In this case, it's only going to grab the first one, right? Because this first one happened. Are people cool with this so far? So once again, this is a linear search. Right? It's solving a limitation in dictionaries. Right? The limitation is we can't really get the key instantly from a value. Okay, well, once again, that's a linear search. Okay, let's move on to the next one. So we got a few more minutes left in class. So let's go through this next one, and then on Thursday, we'll do some homework hints. All right. This next one is asking us to write a function that counts up frequencies of letters. For example, if we had a string called hello world, we should be able to write a function that counts up all of these letters and store them in a dictionary. Right? In this case, this dictionary is kind of saying, hey, H, right, there's one of them. Right? Yeah, that makes sense. There's an H here, and an L, right? There's 3 of them. Right? So that's kind of the goal here. Right? Well, once again, let me just put a small example here. Like, let me just hard code a random string. A random string is equal to hello world. How are you? Just a random string. Basically, the goal is if we were to pass it into some function called count letters. Right, so let me pass it into this. This function should return a dictionary that represents the frequency of every single letter. Right, that's what it should do. So it should return a dictionary that looks something like this. All right, so here, let's go ahead and get that started. So let me go ahead and, oh, okay, you can ignore this example text for now. I'm gonna rearrange something in just a bit. Let me create a function called count letters. Right, define a function called count letters. All it does is takes in a string. Right, so I'm gonna put text here, call it text. Right, the goal is it should create a dictionary and return it in the end. Right, so I'm gonna initialize a dictionary. I'll just call it a frequency of characters. Frequency of characters. I'm just going to set it equal to an empty dictionary, and then in the end, I'm going to return it. All right. Once again, dictionaries use these curly braces. So we need to iterate through this whole text. Right? We need to iterate through the whole text and update this dictionary. Right? So here, let's let's iterate through the text. Right? So for letter in text, right, basically a text, when we're iterating through a string, right, each value will be a character, right, a single letter. So we're going to go for letter in text, and maybe we could update the dictionary. Right? We could do something like, we could say the frequency of character, right, at this letter, right, we could say plus equals 1. Right, by the way, plus equals 1 is the same thing as saying, add 1 to its current value. Right, so it's the same thing as this line right here. Right, that these two are equivalent. Right, but we're probably going to get some weird error here. Right, let's see what's going to happen. Right here, let me just use this next one because it's more readable. Right, but they are the same. Okay, so let's test this. This is saying for each letter in the text, right, increment that frequency by 1. Okay, this is going to look weird though. We're going to get a key error, right? It might seem a little weird on what's happening, right? Basically, it says key error H, right? This is saying H doesn't exist in the dictionary, right? So this is like, here, let me invoke key error real quick. Right? This is like saying test dict is equal to empty, right? And this is like saying test dictionary H, right, is equal to test dict H plus 1. This is going to give us a key error, right? It's a key error because we didn't initialize H yet, right? There's no key value pair that has an H in the key. So one way we can fix it is with a condition, right? We could say if it doesn't exist, right? If the letter doesn't exist, right? So one way we could say that if letter, I think we can say if not letter in frequency of characters. Right? This is saying if the key doesn't exist, then let's make it exist. Right? So I could make it exist by saying set it equal to 0. Right? So this is saying if it doesn't exist, then initialize it to 0. Right? This is inserting a new key value pair. Right? So if it doesn't exist, we'll insert a new key value pair. Else, we can update it. Right? Else, we can update. This is saying increment the current value. Right, so let me just comment this. All right. So yeah, let's test this. There we go. And then let's run this. And oh, what up? Oh, the frequency character not defined. I think I typed it in wrong. So let me see what I typed in. Frequency if. Basically, I'm trying to say if the key doesn't exist. So if letter maybe is, oh yeah, frequency of chars. There you go. I just spelled it wrong. So this is saying if the key doesn't exist in the dictionary, right? The key doesn't exist in the dictionary. We're going to insert a new one. Okay, let's test it. Press play, and there we go. Right, so it's counting up everything. Right, there's H. Oh, we actually should have initialized it to 1 instead of 0. My bad, because there is technically 1 H. So we should initialize this to 1 instead. Because if we found a brand new unique letter, yeah, we found 1. Right, else, if it already exists, then we can just increment it. Okay, let's test it again. There we go. All right, there's 1 capital H here, a 2 lowercase e's, and yeah, a bunch of it. Okay, hopefully people are cool with this. So if anything, you just have to treat each character as a lowercase. And yeah, you can pretty much handle that with some function called lower. Okay, so here, we just finished the rest of this lesson and the lab. Once again, loop algorithms is pretty important stuff. I recommend, for a good practice, I recommend kind of deleting this solution and trying it out yourself. Right? This would be a good practice for the final exam, and also interviews too. Right? A lot of coding interviews will ask folks to write a loop that solves a problem. Right? Most likely, you're going to be getting a problem that's saying, "Hey, here is a list. Can you make me an algorithm that goes through a list and calculate something from it?" Right? That's typically what a first round coding interview can look like. So yeah, loop algorithms are very important stuff. It's a very big takeaway in programming. It's the art of representing a solution in a series of steps. Okay, here let's summarize what we did so far. We finished lesson 17, lab 17 as well. On Wednesday, we're going to jump into the next assignment. The next assignment is Major League Baseball players. So I highly recommend folks take a look at it first, and then we'll give some sneak peeks into it. It's one of the harder assignments. So yeah, have a great day, everyone, and thank you all for coming.